So guys, good evening everyone. Welcome to the session and welcome to the India's most comprehensive preparation platform, that is the BYJU'S Exam Prep. Yes guys, the session is now live and welcome to the next class of Electromagnetic Theory series. Yes, the session is live. Quickly you can update your students, your friends that yes, we are going to begin up the discussions. We are going to begin up the discussions of electric flux and Gauss law, one of the very important topic, that is the Gauss law, which is eventually one of the Maxwell's equation also. We are going to see that in this particular class. Very good evening. I welcome you all once again and let's get started with the session. Sorry for a slight delay. There was some technical constraint I was facing, due to which I was not able to go live, but yeah, immediately very shortly the problem was rectified and we are now live and we are going to begin up our discussions of the very important. Okay, first in this class I shall explain you what flux actually is, what actually is electric flux, and then we are going to talk about this very important Gauss law. So I am telling you very important in the sense that it is important part of the entire course of EMFT, and other than that, very normally you can expect the question from Gauss law in the GATE examination or other competitive examination. Yes, from question point of view also it's an important thing. Okay, so let's get started with this. In case somebody new to my session, this is a brief intro about me. This is your mentor and educator Rakesh. I have secured All India rank 9 in the GATE examination, completed my masters from Indian Institute of Science, Bengaluru. My major area of expertise will include control system, digital electronics, EMT, signal and system, and in the general area, I deal with the maths and aptitude for all branches also. Right. Good evening Karthikeya, Dreamer, Sanjay, very good evening all. Right, this is an update for you guys, since you are all ECE students, maybe IN students. So for the ECE IN students, let us have the analysis of what is the syllabus. Let us have the analysis of what is the syllabus, and out of the syllabus, how to be selective, how to do the smart work, what are the most important topics, right? Really, the smart work is required in the preparation of competitive examination. Hard work and smart work combination is there. So what are the most important topics for ECE that you should never miss out, right? What should be your detailed study plan from now on to secure AIR under 100? So three important things we are going to cover up in the syllabus in this session. The important topics, syllabus, and the rank under 100 strategy. From now on, what should be the study plan? And then this me along with your favorite Rakesh Sir, we are going to be together right on this Thursday. We are going to be together on this Thursday at the same time of 9 p.m. Okay guys, chalo. So join me live with this particular session, Thursday 9 p.m. along with Rakesh Sir. Okay, so now let's talk about, to understand the concept of flux, let us talk about the Faraday's experiment. What actually Faraday's experiment, what was the conclusion, what led to the development and thought process about flux, and then what actually led to the development of Gauss law. All those things we are going to summarize through a single experiment, right? Have a look into this. Right. So if you are able to see in this apparatus, I'll explain you in complete detail, but first have a look into this apparatus. He had a pair of two concentric spheres, right? But one of them was a solid sphere and another one was constructed as two hemispheres, right? That means there should be a sphere, there should be the outer sphere, which we are going to call it as the outer sphere, which can be declaimed into two hemispheres, something like this. I've just taken a simple arrangement what I could arrange here right now, right? So something like this, this is not perfectly a hemisphere, but you can imagine it, okay? So there are two hemispheres which can be clamped, which can be declaimed, right? Clamped as well as declaimed, right? And initially they are discharged. Initially, intentionally they were discharged by grounding it, right? Okay, so he grounded them and this is discharged right now, right? Now concentric to it another inner sphere. This will be known as inner sphere, right? This is not metal right now, but actually it should be metal, right? Right now I did not have any metal ball here. Okay, so yeah, imagine it to be a metal ball and it has to be concentric, and this is a solid sphere. This is not like two hemispheres. This is one solid sphere which is going to be placed inside the outer sphere and it has to be concentric with it. Now, whatever is the gap between the inner and the outer sphere, whatever is the gap between the inner and the outer sphere, it could be simply air, means nothing is there, or it could be any dielectric. Maybe air or any other dielectric can be filled, right? Faraday took around 2 centimeters of the gap between them, between the inner and outer sphere. So I'll repeat, I have 2 concentric spheres. Inner one is a solid sphere and outer one can be constructed using 2 hemispheres. The hemispheres can be clamped and declamped as and when you require, right? The outer sphere was initially discharged, okay, by grounding it, and then this inner sphere was given a known positive charge, right? Known positive charge, which you must be knowing it earlier. Suppose you give it a charge plus Q. So this inner sphere is given a charge of plus Q, a positive known charge. It is placed concentric to the outer sphere and the outer sphere is closed. The hemispheres are clamped and outer sphere was initially discharged. Now, after closing this apparatus, what Faraday found? What was the development of Faraday? Faraday found, to his surprise, that initially this was discharged. Only the inner sphere, which is inside, was charged to the charge of plus Q. This was discharged, but soon after some time, the outer sphere, the inside of the outer sphere, iska jo andar wala structure hai, the outer sphere also developed the same magnitude of charge on its surface. The outer sphere also developed the same magnitude of charge, although opposite sign, minus Q. If this was given the charge of plus Q, this developed minus Q, but the magnitude was same. So outer sphere also developed the charge minus Q over its surface. Okay, so this is what I've already described. Faraday had a pair of concentric metallic spheres, outer one of 2 that can be constructed using 2 hemispheres, right? Inner sphere was given a known positive charge. That is what is the first thing I told you, right? The hemispheres were clamped together around the charged sphere with about 2 centimeters of dielectric material. The dielectric could even be air also. The outer sphere was discharged by connecting it momentarily to ground. It was grounded and hence it was discharged. The outer space was isolated and negative induced charge on each hemisphere was measured. Results: Faraday found that the total charge on the outer sphere was equal in magnitude to the original charge placed on inner sphere, regardless of the dielectric. As I told you, be it any dielectric or be it even air, the charge that was developed over this outer sphere, which was measured afterwards, came out same in magnitude as that of the inner sphere. This was given a charge plus Q. This surface obtained the charge minus Q, although it was initially discharged, right? What does this conclude? It simply concludes that there was a discharged body and there was a charged body and there was some gap between them. This was charged with the charge of Q, and the same charge, after the apparatus was closed, the same charge appears on the outer sphere also. Now this led to the thought process that since there was initially no charge on the outer sphere, so there is some sort of movement. Listen to the important words. There is some sort of movement of the charge. There is some sort of the movement of the charge, of the electric charge, from the inner sphere to the outer sphere, isn't it? Because outer sphere was discharged. It was intentionally connected to the ground, but still it developed the charge. The reason is it had the inner sphere which had the charge Q, and the inner charge, because of this inner sphere charge, the outer sphere developed the charge. That shows the movement, that there is the movement of this inner charge, right, towards the outer sphere, right? This movement of electric charge basically led and gave the theory of electric flux. Let me tell you what is in general meaning of flux. If you open the dictionary or if you Google it up, what is the general meaning of flux? Forget electric flux or any type of flux. What is the in general meaning of flux? Flux represents movement of something. Basically, in simple word, flux represents movement of something. The flux represents the movement of something. And here there is clearly the movement of electric charge, and hence We called it as electric flux. So he concluded that there was some sort of displacement, movement, right, from the inner sphere to the outer sphere, independent of the medium between them, and this movement was referred to as displacement flux, or very commonly electric flux. Right, very commonly electric flux. So what is basically electric flux? In simple words, you can say it is the movement, flow of electric charge from one charged body to the another. And because it is the movement of charge, so flux is measured in the unit of coulombs. What is the flux? Flux is movement of electric charge. So flux is basically equal to the Q, right? How much flux developed on the outer sphere is equal to the charge on the inner sphere, right? So what is Xi? It is directly equal to the Q, and hence units will be equal to coulomb. Hence the unit will be equal to the coulomb. Hi Rongola. Hence the unit will be equal to the Q. That is what is basically the concept of electric flux. Now let us carry forward with the calculations. So if I have look into this picture, if you have a look into this picture, this is what is basically the inner sphere having the radius A, and then there is the outer sphere having the radius equal to the B. Right. What was the charge that was given to the inner sphere? Plus Q, but outer sphere was initially discharged. But later on we found that the surface of the outer sphere also developed a charge which is equal in magnitude but opposite in sign. So what is the charge appeared on this outer sphere? Is minus Q. Right. There is some dielectric material separating the two spheres, but irrespective of the dielectric, whatever may be the type of dielectric, the same amount of charge, the same amount of, we will say now flux, the same amount of charge or the same amount of flux, right, moved from inner to the outer. That movement is the flux. So how much is the flux? The flux is equal to the Q. Right. The flux is equal to the Q. Now listen to some more important terms. Let us summarize everything and then we'll go for the questions also. Right. So if I talk with respect to the inner sphere, dhyan dena. If I talk with respect to the inner sphere, Xi coulomb, as I told you, the unit of flux is going to be coulomb. The Xi coulomb of flux are produced by a charge Q. Who produced the flux? Basically the charge Q, and that is why we have written Xi is equal to the Q. Are produced by charge Q, and that charge is distributed uniformly over the surface having an area 4 pi a square, right? Because I have taken the radius of the inner sphere as A. And what is the surface area of a sphere? It is equal to 4 pi r square. So 4 pi a square. So at the surface of the inner sphere, what is the flux density? At the surface of the inner sphere, what is the flux density? The flux density will be basically named as the total flux is divided by the surface area. The total flux divided by the surface area, and that is equal to 4 pi a square. Xi is divided by the 4 pi a square. That will be the surface density. That will be the flux density at the surface of inner sphere. Right. Now, the same charge due to the movement of charge due to the flux, the same charge moved towards the surface of the outer sphere. So, how much is the density of flux? How much is the density of the flux at the outer sphere? So, outer sphere, same charge Xi equal to Q moved, but the density will be different because the density means flux per unit surface area, and the surface area of the outer sphere will be 4 pi b square, and b is greater than a because it is the outer sphere. So surface density at the surface of outer sphere is Xi upon 4 pi b square, and surface density at random at any point, if you take any spherical body between them, if you assume that there is any more sphere, right, at a distance r, let's say this is the general radius r, what is the density of flux at this surface? So at this surface, the density of flux will be flux upon surface area, that is Xi upon 4 pi r square. That will become Xi divided by 4 pi r square, right? Okay, so density of flux at the inner sphere is Xi upon 4 pi a square, and the density of flux at any surface will be named as electric flux density, which will be represented by D. which will be represented by D. Direction पे हम आएंगे, the direction will come to it. So the flux density at the inner sphere is xi upon 4 pi a square, and xi is basically equal to q. The density of the flux at the outer sphere, xi or q, whatever you write it as, upon 4 pi b square, right? Direction I'll explain you, don't worry, right? And whenever you assume any sphere which is having the radius between A and B, the density will be q or xi upon 4 pi r square, as I have just written, xi upon 4 pi r square. Now guys, what is in general the density of flux? What is in general the flux density? Oh, my screen is off. Just a second, guys. My screen is off. Let me just allow me a few seconds. Okay, yeah, cool. Right. So at any radius between A to B, the density of flux is q upon 4 pi a square. Okay, now let's imagine, okay, there is an outer sphere, there is an inner sphere, right? Now let's make, everybody try to listen carefully. Now let's try to make the radius of this inner sphere small. Okay. So now you have a sphere which is very small in diameter. Something like I had a very small radius, very small diameter. Now imagine that the inner sphere is very small, that is, its radius is negligible, but still that inner sphere is given the same charge of plus q. It is still given the same charge of plus q. So now let us imagine inner sphere, radius very small, charge plus q, and then there is the same outer sphere, right? And then there is a dielectric material which could be even air or anything between them, but it will lead to the same thing, na? Whenever you pack the outer sphere, there will be the movement of charge plus q from the inner sphere to the outer sphere, and the same magnitude of charge appears on the outer sphere. Okay. So if you make the radius of this inner sphere very small, see, if you keep making the radius very small, let me show you in different pictures. Try to listen and answer me one important thing. If you now keep making the radius very small for the inner sphere, right, and if you take very small radius, eventually, if you take very small radius but maintaining the same charge over the surface of the inner sphere, but since the radius is becoming very small, eventually for us it looks like a point charge, isn't it? Eventually what you are able to see is something like a point charge. What is a point charge? A charge which is negligible in dimension, right? Whose dimensions are negligible. So when you decrease the radius but maintain the same charge, it just looks like a point charge. Isn't it? It just looks like a point charge. Okay, it was just looking like a point charge, right? So when radius you decrease, this is the effect you say, eventually you can call it as a point charge, right? But it had the same charge, and because of the flux concept, again that same charge will be appearing on the outer sphere. Okay, but now the radius was small, so it is appearing like a point charge. So for a point charge, right, okay, so if inner sphere becomes very small but having the same charge, it becomes a point charge, but the flux density is still q upon 4 pi I square. But now if it is a point charge, guys, we know from our previous class, okay, we had two classes, Coulomb's law and electric field concept. So what is the electric field intensity due to a point charge? Let us only talk in terms of magnitude, right? In terms of magnitude, to E is equal to Q divided by, what was the electric field formula? Basically KQ by R square, the magnitude KQ by R square, or K is 1 upon 4 pi epsilon naught, assuming free space right now, into Q by R square, or you can say that Q upon 4 pi epsilon naught R square. Now what is the relation between the flux density and the electric field intensity? What is the relation? It is very, very clear that if you just multiply this by epsilon, epsilon and epsilon will get cancelled. And when the epsilon will get cancelled, you get Q upon 4 pi r square, which is the flux density formula. Which is the flux density formula. Which is the flux density formula. So, when this electric field, when you multiply by epsilon naught, you get D. Right? You get D. So, D is equal to epsilon naught E. D is equal to the epsilon naught E, where epsilon naught is the permittivity for free space. This is the permittivity for free space, or if there is any other general, any other medium, right? If there is any other medium, epsilon naught is the permittivity with respect to the free space, right? So, for other medium, D will be written as epsilon E, right? We know epsilon is a scalar quantity. We all know that electric field is a vector quantity and electric flux density hence is also a vector quantity, and the direction of the D will be just parallel to the direction of E. D will be equal to epsilon E, where epsilon is the permittivity of the medium. Epsilon is the permittivity, electric permittivity of the medium, which is given by what formula? Epsilon permittivity of any medium is the permittivity of free space into epsilon r, where what is epsilon r? Where what is epsilon r? Epsilon divided by epsilon naught. Epsilon divided by epsilon naught, that is the permittivity of the medium compared with the permittivity of free space, and this is known as the relative permittivity. Epsilon r is known as relative permittivity for any medium, which is the permittivity of that particular medium divided by the permittivity of free space, right? Free space, right? So that's what, no, we cannot say it's going to be infinite. Satish, I'll tell you the logic behind this. Won't be any electric field inside metal, no? How inner sphere is it? No, Ruby. Inner sphere, the surface of this inner sphere, Ruby. The surface of this inner sphere was given the known charge, the outer surface. I'm not talking about the internals of that. The outer surface was given the charge intentionally, right? And that led to the movement of charge from the inner to the outer sphere, Ruby. Satish, see. Radius, first of all, I'm not making it exactly 0. See, point charge is something which has negligible, smaller dimension, right? So I'm not telling that R will be 0. R will be small. What I'm telling is R will be small. Now, still you think that electric field, this D will be large? No. See, what is this? This is Q. And Q, usually, you know, the charge. See, even 1 coulomb of charge is a very huge amount of charge. Usually, the charge can be in the form of microcoulombs or nanocoulombs. So, don't worry. This is, you know, usually the charge is a very small quantity and the flux will not be that very large. Satish. Okay. Chalo. Okay, guys. Okay. So, we also have a relation between D and E. We also have a relation, this important relation between D and E, that is D is equal to epsilon E, and once again I repeat because epsilon is a scalar, epsilon is a constant, so D will be parallel to the E, right? So D will just follow the direction of E. Okay, so just if you know about electric field, what we learned, right, whatever is the direction of electric field. Okay, yesterday in the last class we learned the electric field due to point charge. Mostly we were focused on that. But what is the electric field due to line charge, surface charge, volume charge? This all I will cover through the application of Gauss law. That will be in the tomorrow's class. Tomorrow we will today we will conclude Gauss law with some questions. Tomorrow application of Gauss law, right? And with that you will learn the electric field due to line, surface and volume charge. Whether it is point charge, line charge, surface charge, volume charge, whatever is the direction of electric field, same direction will be followed for the electric flux density. Okay, sir. Okay, let's move ahead then, right? Now, if you know, flux, I have defined, flux density, I have defined. What was the flux density? The flux density, total flux divided by unit surface area. Now, suppose I now know the relation between D and E. So, I can calculate the flux density easily. Electric field we have understood in the last class. Knowing the electric field, I can calculate the flux density, and once I know the flux density, what is the total flux crossing any surface? What is the total flux crossing any surface? It is the surface integral. It is the surface integral of the electric flux density, because flux density is flux per unit surface area. Integrating it for that entire surface, some surface whatever is given, calculate the flux crossing any surface, right? You get the total flux. We'll see such questions. Okay, right now we were interested, right now the problem was simple. We were trying to calculate the flux that is developed over the sphere. Not only sphere, it could be any other surface. And what is the total flux crossing that surface? Okay, to calculate that, we can use the formula integral D dot ds, surface integral of the flux density vector, where the flux density vector, we can also write this formula as epsilon integral E dot ds, because the flux density vector is directly equal to epsilon E, right? Yes, will come, Anko. That's what application of Gauss law is there tomorrow. And that is why I have separated the class, the basic formulation of Gauss law and then application of Gauss law coming up tomorrow. The application of Gauss law you'll see with examples tomorrow. Okay, you'll see with examples tomorrow. Don't worry regarding to it, right? Okay, sir, let's move ahead. Okay, now Gauss law. Okay, the Gauss law, which is going to very soon now going to give you one of the Maxwell's equation. Okay, the Gauss law, which simply states that Gauss law is just a proper conclusion of Faraday's experiment. Faraday did the experiment, Gauss properly stated and formulated it, and hence commonly in this day we call it as the Gauss law only, which says that the total electric flux through any closed surface, is equal to how much? Now let's have a look into this. Let's have a look into the Faraday experiment once again. What was the total electric flux that was over this outer sphere? What was the total electric flux that was crossing this outer sphere, which is closed? Of course, closed surface is very important. So what is the total electric flux which is crossing this sphere? Is how much? How much of the flux was equal to Q? Why it is equal to Q? Why it is equal to Q? Because there was a charge Q that was applied on the inner sphere. Inner sphere is inside the outer sphere. So in short, I can say that how much is the flux that is crossing the outer sphere is equal to the value of the charge that is enclosed by this sphere, is equal to the value of the charge. This surface, this outer sphere, inside has a charge enclosed that is equal to Q. And whatever is the charge that is enclosed by this surface, same amount of flux is crossing that particular surface, and that is what is simply known as the Gauss law now, which has just been come up on the observation of Faraday experiment, right? The total flux crossing through any closed surface is equal to what? Whatever we just observed is equal to the total charge enclosed by that surface. उसके अंदर जितना भी charge होगा, we are going to take the questions based on this, don't worry, right? Total charge enclosed by that surface equal to total charge enclosed by that surface. So total flux crossing any closed surface is equal to the total charge that is enclosed by that surface, is equal to the total charge that is enclosed by that surface, right? Right. Any confusions up to this point you can say, or else let us continue to complete up to the Maxwell's equation also, then we'll take up the question, right? Right. Okay. There are several ways of it, Ankur. Okay, no specific. You can charge up a body through different methods, and that's a different case. We can discuss it maybe sometime later. Okay. So Q is equal to the charge enclosed. So there are several ways of charging the bodies, right? Okay, thank you, Chetan. So Q is equal to the Xi is equal to Q enclosed. Now let's move forward. The Xi, as we know, can be calculated as, the Xi, as I just told you, can be calculated as the surface integral of the D vector, integral D dot ds. Acha. The Q enclosed, the charge can also, Xi is equal to Q, and the Q can be calculated if we know the volume density of that particular medium. Now I introduce one more term here, right? Rho V, that is known as the volume charge density. This is the properties of material, volume charge density of the medium under consideration. So there are some properties of medium that you must know before studying it. So I'm just pointing out that right now. Rho V is the volume charge density of the medium measured in Coulomb per cubic meter. measured in the coulomb per cubic meter. Coulomb per cubic meter, right? So Q can be, now because it is the volume charge density, charge per unit volume, so volume integration of rho v will give you the total charge, and if I equate both of them, xi is equal to Q enclosed, xi can be obtained as integral d dot ds, Q can be obtained as integral rho v dv. But if you have observed, there was one very important line in the Gauss law. What was that important line? The total electric flux crossing any closed surface. The total electric flux crossing any closed surface. Very important point. Through any closed surface. So whatever flux we are calculating is through a closed surface, and for closed surface integral we just put the symbol of closed surface, and whenever there is a closed surface you apply the Gauss divergence theorem. So little bit mathematics you have to just mix here, right? Little bit mathematics you have to fix here. Gauss divergence theorem, guys, you study in the vectors. You study this in the vectors. Gauss divergence theorem. That is also named on Gauss only. That is also named on Gauss. What is the Gauss divergence theorem? For any closed surface, integral f dot ds, let f be any vector, integral f dot ds, the surface integral of a vector function is equal to volume integral, of divergence of f, right? I know you guys may or may not have studied vectors till now, right? So whenever some vector calculations were required in the Coulomb's law in electric field class, I briefed you about that, right? If you are stuck in the divergence f, I'll help you, don't worry, I'll give you all the required formula of vector, right? So this is equal to integral divergence. Divergence is represented as del dot f dv, right? So if I come here, because this is a closed surface, applying the Gauss divergence theorem, I can write it as integral del dot d dv, that is the volume integral of del dot d, and that is equal to integral rho v dv, where rho v is the volume charge density. Now both the sides I have converted to the volume integral. Right, and hence their integrands can be compared, right? So when you compare the functions of integral, what are the functions on the left hand side and right hand side? You can say that del dot d is equal to rho v. Del dot d is equal to the rho v. Del dot d is equal to rho v. Del dot d is equal to rho v. Del dot d is equal to rho v. The first of the Maxwell's equation. First as in first for our sequence. See, there is no logical sequence behind Maxwell's equation. First means whatever we have studied till now, according to that, it is the first of the Maxwell's equation coming in front of us. That is the del dot d equal to rho v. Right. One of the Maxwell's equation, you can say. First or second se itna matter nahi karta. Right. So here the Gauss law itself ultimately is one of the Maxwell's equation, very important for competitive exam. Directly you can expect the question based on this, right? Now rho v is equal to del dot d. Okay, if you are troubled, if you are not able to recall the formula for divergence, I will tell you, right? Rho v is equal to del dot d. Rho v is equal to del dot d. But what is the divergence formula? Right, what is the divergence formula? So for that, the vector that can be given to you can be in the Cartesian form. In the Cartesian form, you write down the vector as breaking into the xyz component. Dx ax, dy ay plus dz az, right? What is the del dot d? It is simply given by del x of dx, del y of dy plus del z of dz. All right. If the vector is expressed in the cylindrical coordinates, in the cylindrical coordinates you have rho phi z, the components rho phi z, d rho a rho plus d phi a phi plus dz az. In that case, the divergence formula is given as, 1 by rho del by del rho of rho d rho plus 1 by rho del by del phi of d phi component, differentiation with phi of the phi component, plus del by del z of the z component. That is the formula that is to be used in cylindrical. And if the vector is given in the form of spherical coordinates, if the flux density vector is given in the form of spherical coordinates will comprise r theta phi, right, to dr ar plus d theta a theta plus d phi a phi plus d phi a phi. The divergence of d in that case is given by 1 by r square del by del r of r square dr plus 1 by r sine theta. With practice this will set in the mind. 1 by r sine theta del by del theta of d theta multiplied by sine theta, d theta the second component, and finally you have 1 by r sine theta del by del phi of the d phi component, del by del phi of the d phi component. These are the formulas for your reference that you study in the vectors, vector calculus, right? And since right now we are studying the electrostatics part, so I've just briefed you whatever is the formula that may be required. Okay, now let's take some problems. This part is done, this part is done. Now let's take some problems. Okay, so there are two, actually, the concept of flux I have described you, then we came to Gauss law, eventually leading to the Maxwell equation. What are the two important formula where you can expect the questions? I will tell you. One formula is directly this one, xi is equal to q enclosed. The total flux crossing any closed surface is equal to charge enclosed by that surface. One question you can expect it from this, and otherwise the question that is normally expected is del dot d equal to rho v. Right? The volume charge density of a medium is equal to the divergence of electric flux density vector. Okay. So following point charges are located in air. Okay, there are 3 point charges. What is the total electric flux over a sphere? Right, electric flux over a sphere. Sphere is a closed surface, so we can apply the Gauss law. Sphere is a closed surface, so we can apply the Gauss law. And according to the Gauss law, the total flux crossing any closed surface is equal to charge enclosed by that surface. So the surface is a sphere of 5 meter radius and the center is 0, 0. And the center is 0, 0. Let me just draw the diagram in front of you. Assuming just a freehand diagram, let me take. Suppose this is what is the sphere given to you. Okay, assume it to be a sphere. I am just taking a circular symmetric body here, and the sphere has the sphere. The sphere has the center at 0, 0, and there is a charge as well at 0, 0. Okay, so this point, radius is 5, so this should be 5, 0. Radius is 5 to this point should be 0, 5. Right. Now there are 3 charges given to you. Locate the 3 charges and answer me. What is the total electric flux over this sphere? Answer me this question, guys. Come on quickly. Answer me this question. Come on quickly. Yes, got it? Okay, Ruby gives the answer. So let us locate the charges. 0.08, let's say this is Q1. Let me call this charge as the charge Q1. Let's say this is Q1. 0.05 is Q2 minus 0.009. Let's say this is the Q3. Now let us locate these charges. Q1 is at origin. So this is where is the Q1. Okay, Q1. And then Q2 is 3, 0. Okay, 3, 0 is inside 5, 0. Here you have Q2. 0, 4. Here you have Q4. At the point 0, 4, you have the Q4. Sorry, Q3. You have the Q3. Right, all are enclosed, all are inside. Right, so what is the flux crossing any closed surface is equal to the charge enclosed by that surface. And what are the charges that are enclosed by the surface? All are enclosed. Q1 plus Q2 plus Q3. Right, the value of Q1 is 0.008 microcoulomb, Q2 is 0.05 microcoulomb, Q3 is minus 0.009 microcoulomb. So this is minus 0.001 and plus 0.05. So this is 0.049 microcoulomb is the value of flux. The flux is 0.049 microcoulombs, and option number B is the correct answer. Now listen to me. Suppose there is another charge Q4 which is located here. Suppose there is another charge Q4 which is located outside the sphere. So will your answer be affected? No, answer will still be the same, because the total flux crossing any closed surface is equal to the charge enclosed by that surface. So if there is any other charge Q4, Q5, anything which is outside the sphere, right, that you should not count. That is not to be counted. Okay guys, that is not to be counted. Okay, chalo, that is not to be counted. You have to take care. Okay, now before we take any similar question, let us take one important question here. Why is this not responding? Yeah, now let us take one important question to be discussed here. Given that D is equal to Z rho cos square phi, cylindrical coordinate system is given. Rho phi Z, it's given in the form of cylindrical coordinates. It's given in the form of cylindrical coordinates. Right, the formulas of cylindrical coordinate I already told you. Be aware with the formulas. Be aware with the formulas. I have already told you as a revision. That is why especially look into this. Right, the cylindrical coordinate system. The formulas were already discussed. Right. Yeah, let's come back to this. Okay, the cylindrical coordinate system. Okay, just a second. Correct, it's working. Okay, calculate the charge density at 1, pi by 4, 3 and the total charge by the cylinder of radius 1 meter with the -2 less than z less than 2. Let us understand this. Then we can take a question in Cartesian also, but let us first take up this question. Right, it's directly given to you in the form of cylindrical coordinates. Calculate the charge density. Calculate what? Calculate the rho v at 1, pi by 4, 3, at 1, pi by 4, 3 and the total charge by the cylinder of radius. Total charge बाद में निकालेंगे. Let us first focus on calculation of the charge density. Right? Yeah. So the Gauss law cannot be applied if the surface is not close, Sai Charan. Okay. The total charge density rho v, and what is the formula for rho v? Rho v is given by del dot d. Rho v is del dot d. Del dot d, and that is given by del by del x. Sorry, this is not in the Cartesian form. It is in the cylindrical form, right? So 1 by rho del by del rho of rho d rho, whatever the formula we discussed just now, plus 1 by rho del by del phi of d phi plus del by del z of dz. Now what is the vector given? Have a look into this. What is the vector given to you? What is the vector d given to you? Z rho cos square phi, z rho cos square phi, az coulomb per meter square, charge per unit surface area. That is the formula, that is the unit for flux. Now this is just what component it is carrying. It is carrying only the z component, so it is simply dz az. It is simply dz az. So what should be the calculation for rho v in that case? The calculation for rho v in that case, there is no d rho component, there is no phi component, to 0 and 0, right? Plus the del by del z of the z component, z rho cos square phi, and we all know the rules of partial derivative. This is del by del z, right? So when you differentiate with respect to z partially, rho and phi should be the constant. So rho cos square phi is constant, derivative of z will be 1, so it is simply equal to rho cos square phi. So what is rho v? We get an important answer. Rho v is equal to the rho cos square phi. Rho v is simply equal to the rho cos square phi in the unit of coulomb per cubic meter, because it is the volume charge density. This is the rho v. But the question is asking, calculate the rho v charge density at a point 1 comma pi by 4 comma 3. So let's substitute the value at the point 1 comma pi by 4 comma 3. What should be the value for rho v? At this point, rho v becomes rho, which is 1 multiplied by cos square phi. Phi is pi by 4, right? So this is 1 into cos pi by 4 is 1 by root 2, so 1 by root 2 ka square, and hence the total answer is 1 by 2. So rho v at the point 1 comma pi by 4 comma 3 is 1 by 2, that is 0.5 coulomb per cubic meter. That's your answer number 1. That's your answer number 1. An important type of calculation, an important type of question. Taking the next question now. Also calculate the total charge by the cylinder of radius 1 with the minus 2 less than z less than 2. Also calculate what? Also calculate what? Calculate the total charge. Calculate the total charge. How do you calculate the total charge here? How do you calculate the total charge here? The total charge can be calculated as volume integral of rho v. As I told you the formula earlier, the charge is rho v dv, right? What is the dv? For cylindrical, whatever formulas of vector is required, I'll just keep briefing you, right? And suppose if you guys demand later on, if you guys need later on, we can plan some separate classes of vector calculus specifically for EMT. But right now, let me brief out the formula. The cylindrical coordinate system, the value of dv is written as rho d phi dz. So what is the total charge enclosed? So the total charge enclosed is given by the formula, right? dv means d rho d phi dz, means triple integral will come. What is the value of rho v? The general for the function for rho v is rho cos square phi. Rho cos square phi into rho d phi dz. Multiply rho to rho. So the charge enclosed will be given by the formula triple integral rho square cos square phi, rho square cos square phi d rho d phi dz. Let us separate out all our variables separable. So we have integral rho square d rho, because the limits are constant only. Now see, what is the rho? What is the radius of the cylinder? Radius of cylinder is 1 meter. The rho will be from 0 to 1. Phi, for a cylinder, phi is from 0 to 2 pi always, right? And z is given to be minus 2 say plus 2. Z is given to be minus 2 say plus 2. And always remember, for a cylinder, the range of azimuthal angle is 0 say 2 pi. My screen is once again off. I don't know why it's getting off. Maybe charger is not connected. Yes. Yeah. Okay. Okay, yeah, it's on now. Okay, so let's separate out this integration. Integral rho square with d rho, integral cos square phi with d phi, integral dz. Okay, this is the limit 0 se 2 pi, rho is under the limit 0 se 1 and dz is under the limit minus 2 se plus 2. Okay, rho square integral rho cube by 3, limit 0 se 1, integral cos square phi, as you know, if you have followed any of my previous mathematics session also, especially integral calculus session, I have given you the beta functions. I have also given you the Wallis integral formula, very simple. So integration, I leave it to you. I solve my own technique, because if I go on explaining you Wallis integral formula now, that will take around 30 minutes. So let me just write down the integral answer here. Twice integral 0 se pi and then again twice integral 0 se pi by 2 cos square phi, cos raised to the power m phi, right? So that will be 1 double factorial, which is 1 divided by 2 double factorial, 2 power even hai, so I will place pi by 2, right? Dz integral is z, that is simple, limit minus 2 se plus 2. So now putting down the values, for rho the value upper limit 1, lower limit 0, so 1 minus 0 by 3. Second integral 2 and 2 cancel, the answer is pi. Third integral 2 minus minus 2, answer is 4, right? So 1 by 3 into 4, total answer is 4 by 3 coulombs, 4 by 3 pi coulombs, right? 4 by 3 pi coulombs, 4 pi by 3 coulombs, right? If we want the final numerical answer type range, 4 pi by 3, that is 4.188. 4.188 coulombs. Very similar question, very similar question has been asked in GATE 21 last year for 2 marks. Very similar question has been asked in GATE 21 last year for 2 marks in electronics. And then electronic students looking into the syllabus, they are confused. They are confused whether they have to study this electrostatics topic, whether they have to study this Flux Gauss Law or not. There is a question last year only, GATE 21 for 2 marks. That's why I told you. For ECE also, electrical, this is there. Instrumentation, it is there. But for ECE also, yeah, they have written Maxwell equation. Na? So you have to study the electrostatics and magnetostatics also. You cannot skip it up. GATE 21 2 mark question. Directly. Not this one, but very related. Little bit data and language change. Right? So you just have to, you know, follow this as a part of syllabus. Okay. Chalo sir, let's try 1 or 2 more. The static, now see, it's a GATE 22 mark question. This is for electrical. This was electrical GATE 20. The type of question I was mentioning was GATE 21 electronics question. So every branch can expect such questions. The static electric field inside a dielectric medium with the relative permittivity 2.25, with the relative permittivity 2.25 expressed in cylindrical coordinate system. Once again, cylindrical coordinate system. So see, usually in cylindrical coordinate system, we follow rho phi z. Rho is radius of the cylinder, r is also the radius. Na? So whether they write r or rho, you know, but to avoid any confusion, I can write it like this. E is equal to 2 rho a rho. Let's call it in our regular language. Plus 3 by rho a phi plus 6 az. Right? If the above expression represents a valid electrostatic field inside the medium, then what is the volume charge density? Then what is the volume charge density associated with the field? Right? What is the volume charge density associated with the field? And what is the volume charge density? Again, coming to the Gauss law. Gauss law or Maxwell's equation, the rho v is given by the formula del dot d. But sir, in this question, previous question, flux density was given, d was given. Here, electric field is given. But no problem, na? We can substitute the relation between them. D is equal to epsilon E. D is equal to epsilon E. Epsilon is a scalar constant, so you can take it outside. Epsilon del dot E. This becomes epsilon del dot E. So rho v is equal to the epsilon del dot E. Rho v is equal to the epsilon del dot E. Right. Now, what is del dot E? पहले हम E को लिख लेते हैं एक बार. What is E once again? 2 rho a rho plus 3 by rho a phi plus 6 az, and the formula as I just revised for you. Let us once again use the formula. Divergence in cylindrical coordinate systems. The divergence formula in the cylindrical coordinate systems, 1 by rho del rho of rho d rho, the rho component, plus 1 by rho del by del phi of the phi component, and the phi component is 3 by rho, plus last is del by del z of the z component, which is 6. Now see, 2 rho square, differentiation of rho square with rho will be 4 rho, will be 2 rho. So ये हो गया 1 upon rho, differentiation of rho square is 2 rho, but 2 2s, it will become 4 rho, right? Plus, now have a look into this clearly. Differentiation with phi of a rho function. When you are partially differentiating with phi, rho is a constant, so differentiation 0. Differentiation of 6, which is anyways a constant, is 0. So second and third term is 0. First maybe rho cancel, you get the divergence equal to 4, right? You have obtained del dot E equal to the 4, right? So now what is the rho V? Rho V is epsilon del dot E. Rho V is epsilon del dot E, so that becomes 4 epsilon. That becomes 4 epsilon. Now here I have seen students many a time that students just mark with the option A and then leave. They mark confidently option number A, they leave the question thinking that they have scored 2 marks, but actually they will score minus 2 by 3. They will go into negative marks. They will go into the negative marks. Sir, why? Because the medium here is not free space and it has a relative permittivity 2.25. So answer is 4 epsilon. It is not complete. What is the value of epsilon? Epsilon for any medium is the relative permittivity multiplied by the permittivity of free space, and relative permittivity is given to you as 2.25. Now when you multiply 4 into 2.25, that turns out to be 9, and your final answer is 9 epsilon naught. Your final answer is known as 9 epsilon naught. That is the answer. So your correct answer is option number D. Okay, so be very, very clear and very, very specific. The permittivity, whether it is given for the free space or whether it is given for any other material, if there is some relative permittivity given, and etc. Okay. Chalo. In a region D is equal to xax plus yay plus zaz, just like the general position vector, what is the flux radiation out of a sphere of radius 1 meter centered at the origin? Yes, spelling mistake hai. Centered at the origin. What is the flux radiation out of a sphere of radius 1 meter centered at the origin? Flux radiation. D is given to you. D is given to you. Right? See, the flux radiation, the question, concentrate on the question. Flux xi integral d dot ds, right, over a closed surface, but that is also equal to integral rho v dv. That is what we have learned, na? That is what we have learned. Okay, one formula is this. One is applying the Gauss law. Gauss law will make the problem simple. Gauss divergence theorem will always make the problem simple. So flux is equal to charge enclosed, and charge is given by integral rho v dv. Now how to calculate rho v? Rho v is the divergence of d, and this question is simple because rho v, Maxwell equation, divergence of d, and this question is simple because the d that is given here is in Cartesian coordinates. Here the d that is given to you, it is in the Cartesian coordinates. It is in the Cartesian coordinates. So if I substitute the value, rho v del by del x of the x component is x, del by del y of the y component, del by del z of the z component, so it is 1 1 1, final answer 3. Rho v is equal to 3. So I've got the rho v. So what is the total flux? As I am able to see, it is integral rho v dv, but here rho v is a constant, that is equal to 3, so it is 3 dv. Constant is outside the integral, you get integral dv, right? And integral of dv, integral and d cancel, you just get v. Integral of dv is always equal to the volume of the region. What is the region given to you? It is a spherical region, right? So here volume means volume of sphere. Here volume means volume of sphere. So 3 into 4 by 3 pi r cube, volume of sphere is 4 by 3 pi r cube, 3 se 3 cancel, 4 pi r cube. Radius of the sphere is given to you 1 meter, so 1 cube is 1, and the total answer should be 4 pi. The unit of flux is same as unit of charge, that is coulombs, so answer should be 4 pi coulombs. Option number D. Navneet, check your calculation once. Option number D. Answer is 4 pi coulombs. The correct answer is 4 pi coulombs, everybody. The correct answer is 4 pi coulombs. That is why, guys, I told you in the very beginning also, right, to have a strong grab on this subject, to strong hold on this subject, basically you should be remembering all the fundamentals of vectors, right, all the fundamentals of vectors, right, all the formulas related to it, and you should be little bit good in handling the double and triple integrals, the multiple integral cases. If that part is there, then EMT is mostly it is concept based, but formulas and calculations that is coming behind the cal stage is mostly the vector and related terminologies. Okay, so be aware about that. And with this, let me give you one homework assignment for today. If D, that is the flux density, is again given to you, this time again the question it is in Cartesian, so calculations are relatively simple. If D is given to you, find the volume charge density rho v, right, and calculate the flux through a cube, right, and calculate the total charge. Okay, dekho guys, this is same only, right, B and C, the flux is equal to total charge enclosed by the cube, so that is same. These two are eventually same. These two are eventually going to give you same. So why I have written two different questions? Just to give you the feel that, yes, the question, language of the question can be totally different, right? It is a question which I have taken from Sadiku. I told you one of the best book for you is Sadiku, but yeah, if you are following these classes, then probably I am making your way things simple. No need to refer the books. You can just follow this content and get your problem simplified in the simplified manner. Acha, so xi is equal to q enclosed, and finally how you are going to solve it up? Integral rho v dv. Just like the previous question, solve it up as integral rho v dv. What is rho v that you will calculate in the first part, right? What is rho v that you are going to calculate in the first part? Rho v is the divergence of D. Simple formula because it is Cartesian. What is dv? In the Cartesian coordinate, dv is given by dx dy dz. That's it, right? Okay, chalo. So this is one homework assignment for you. It is very similar to one of the question that we solved earlier. This question we solved, na? It is simpler than that because we have solved a question in cylindrical. See, similar question. Given the D, first calculate the volume charge density and then calculate the total charge enclosed by the cylinder. Same question, very same question, the same approach. You can just follow this question. Calculations will be a little more easier because cylindrical, rather than cylindrical, I've given you a very regular Cartesian coordinate problem, right? So very similar to this, very similar to this, and this is the homework assignment for you for today. Right? Please do not forget to solve it up, and once again the reminder for you that all ECEEIN students, what are the most important topics for you from the entire syllabus? Smart work you have to do, right? You have to study the entire syllabus, but you have to practice more on the most important topics. Then what should be a study plan from now onwards, right? Since July is approaching, to secure AIR under 100, me along with Fanindra Sir, right? We are both coming live Thursday. At the same time of 9 p.m. Stay tuned to BYJU'S Exam Prep. Stay subscribed and enjoy all such sessions, right? And tomorrow, guys, what is the class? Tomorrow at the same time, that is the 9 p.m, we will be continuing and talking about the applications of Gauss law. The applications of the Gauss law. Okay. Tomorrow, same time, application of Gauss law, and where we'll especially talk about the line charge, surface charge, volume charge, whatever we studied today, what is the application and how it can be used to simplify several important type of charge distributions. With this, I, Rakesh Sir, sign off for the session. Keep studying. All the best for your preparations, and let's meet tomorrow at 9 p.m. for application of Gauss law. Bye bye. Thank you. Stay safe. Take care. Good night.